Okay, so good afternoon, everyone. We will continue with lecture 23rd, yet another optimization model, and this time it will be neural networks. So I decided that I will do solvers towards the end. So let me complete this, and along with this, I plan to do stochastic gradient methods. There are many variants of that, so we will try to cover those as well. So let us see what these optimization models are. As you may know by now, neural networks are everywhere now. So it can be used in speech recognition. Okay, so if someone is speaking, then the computer has to recognize what are those words. Okay, so for example, the applications are Siri, Alexa, and so on. Yeah, it's also used now these days in translation. So language to language translation. Okay, so German to English or Hindi to Telugu and so on. Okay, so it can be used for translation task. It can be used for image segmentation task. So here there are a couple of people in the images, and then here the goal would be to identify these objects. Okay, so what are these objects in this picture? So where are the people? So in the box you can see those are being identified by a computer. Looking at the features of these objects, it identifies whether it's a human, whether it's a pushcart, whether it's a building, and so on. Here, like one is trying to identify the model of a car. Okay, so just by looking at these images, because each model comes with its own unique features. So depending on the feature, you will identify which car is which model. Okay, so behind all this is a neural network. Neural networks can also be used in playing games. So the computer can be seen as an agent that can learn the rules of the game simply by watching. Okay, and then it can actually play and even beat. Okay, so now this is what is happening now. For instance, if you can remember some news, there is something called Alpha Zero. Okay, and developed by Google's DeepMind, and they are able to beat the best of the players. Okay, and long time ago, it could also beat the best players in the chess and so on. So these days they can play a game and they can beat. So playing game, as we understand, is not easy. It's tricky, and whether a neural network can understand those details and strategies of a game, that is already a very challenging task. So and it is able to learn without even explicitly telling the strategies to the agent. Okay, it can just watch actually. So from the visual images also it can learn. Okay, so it's quite advanced now, where and behind all this there are neural networks. So these could be developed using reinforcement learning, and then there is an area called deep reinforcement learning where you generate these initial set of level data where it will be the moves that you are doing and then the results that you are getting from your moves. So initially, obviously, these agents will fail a lot of times, and then there will be times where it will also succeed. Okay, although initially it may just play randomly. So with this, you may feed into these neural networks and so on, and then let the neural network also update the weights of the, according to the levels that you get. In this case, the levels could be seen as rewards and so on. So there are quite a few things here involved. It's an area called reinforcement learning, where we can. So now reinforcement learning is also used in many other areas, especially in robotics. Okay. Okay, so it can be used in image captioning. So I have a couple of images, and then the goal would be to caption the images. So in this case, For instance, the first figure is like man playing, man in black shirt is playing guitar. Okay, so it's like just from the images, can you guess these texts? Okay, so similarly, a construction worker in an orange safety vest is working on road. Okay, so these are the guesses or the captions generated by the computer itself by looking at the images. In the images, it will extract those essential features. Okay, so in this case, it has to identify the features of a man and the guitar and so on, and then the actions of the person as well. So whether he's trying to play or he's just sitting beside the guitar and so on. So these type of captions may be generated. For example, in Facebook, you upload a photo and then captions can be generated automatically for you. Okay, so let us start with how it all started. So there is something called Perceptron. So Perceptron. So we, as a human being, we have a lot of perceptions. Okay, so there are many things we can perceive. So it could be vision, the things that we see. Okay, so that's a perception, the things that we hear. Okay, and perceptions, it could be touch. Okay, so these are the senses and so on that we can, and based on these things, we identify and classify and so on. Okay, so perception is an important thing that allows us to classify things, obviously, and distinguish and so on. But so what is the basic ingredient that we may need? What would be the basis of all these perceptions that we have inbuilt in our body, basically? Okay, so one can go with the basic element that is needed, and here we can talk about something called perceptron. The definition of this is like very, I mean, it's here. Too many texts are written, but I think we can skip this text. And so these are the texts taken from this paper, but we would like to come back to perceptron a bit later to define. But what is going on in all the images that we have seen? So one is like we can do a transcription, so video signal, and then we need the text images, and then we need the text caption game state, and then we want to know the next move. So in this case, all these we have a box here, and these boxes are what we call a neural network, and we believe that these neural networks are based off some basic ingredients called perceptron. So the question is, what is inside this box? Well, it's some kind of a neural network here. Okay, so these boxes are like a neural networks here, and okay, so where does it all start? It starts with none other than human beings, the thinker. Okay, so so this is the statue of the thinker, okay, by Augustin Rodin. What are the capabilities of humans? Well, they can learn, they can solve problems, they can recognize patterns, they can create something, okay, something useful. Right, but how do humans think? Well, it's not something that we know exactly right now. It's still a work in progress. How exactly we think and so on. Okay, how things get processed in our brain is not very. It's a subject of research. There are still some leads, but we don't know it with a full clarity. Okay. Okay, so what we see is we start from humans, the thinkers, and we are looking up to humans, and we are trying to see what are the things humans can do, and we would like to get some inspiration from there, right? So looking into earlier theories of cognition, so decoding how humans think. How humans think, one example could be that lightning is followed by thunder. So one of the things would be like, well, I saw a bolt of lightning and we are going to hear thunder. Okay, so that's something we relate to. So we relate thunder to lightning, and we just heard the thunder. Did someone get hit by lightning? So these are the questions we relate to. Like if we heard the thunder, then we relate it to a lightning. If the thunder is very strong, then maybe we expect that that maybe the lightning was also powerful and maybe it hit it's somewhere. Okay, we see various news of lightning hitting, and even people die because of lightning. So from here we are trying to build or associate things, right? So we associate, hence we learn pattern. So one theory of learning is like we learn because we associate. Okay, so the pairs of thoughts become associated based on the organism's past experience. Hence, learning is a process that forms association. Okay, so learning, they believe is a process that forms association. So we learn via associations. Okay, in other words, in this example, we see that the bolt of lightning, we expect thunder will follow. Okay, so we have seen this many times, a bolt of lightning and then some sound comes up. So then we know that, okay, a bolt of lightning is associated with thunder. Okay, we also know that we heard thunder, a loud thunder, then it is also in rare cases associated with lightning hitting somewhere, right? Okay, so it is in the most worst case, it may hit and kill some person. Okay, so one theory suggests that we associate, hence we learn. Okay, so that's one theory. So based on this, these associations, so-called association, they came up with 4 laws of association. Law of contiguity. Things or events that occur close together in space or time get linked together. For example, lightning and thunder. Thunder follows lightning, and they occur close in space, relatively closer in space. Okay, and time also. Okay, so when we hear thunder, we also get to sense maybe from which direction it might. Often it's not really known, but in other cases, obviously we know. So it's like if there is a road accident and then something like that, we can somewhat figure out where this sound came from. Okay, so it's like both space and time, or just space, or just time. So things that appear together, right? Bread with butter, maybe. Okay, so that's one also one kind of association, right? Pen and paper. Okay, so perhaps if you remember pen, then you remember paper. Okay, maybe. Okay, so because things that appear together, perhaps we remember them. So sometimes it happens that I remember something because of something else, because they are closely associated to each other. Okay. Okay, so this is one law, where law of contiguity, where we tend to remember things when they happen together in space or time. Law of frequency: the more often two things or events are linked, the more powerful that association. Okay, that's one thing. Like more often I hear the things again and again and again and again, I will tend to remember that thing more and more. Okay, so that's also a natural thing. We all experience this. Practice makes the man perfect, right? So if you keep doing the same thing again and again and again, you become perfect. Okay, and that's how you see the carpenters and so on. If they keep doing the same thing, they are much better than us. Okay, so they are much better than us in the skill. In the skill that they're learning. Okay, we are talking about theory of learning, right? So how people learn. So one way that people learn is like you see or do something again and again, okay, repeatedly. So law of frequency: how frequently things happen also relate to how you are going to learn. Law of similarity: if two things are similar, the thought of one will trigger the thought of the other. Okay, again, if there are similar things, then you tend to remember. Okay, law of contrast, and that's something else now. On the other hand, when things are too opposing, also you tend to remember. Okay, so if something is a completely opposite of that, you will tend to remember. Okay, so these were the 4 laws of Aristotle, the Greek philosopher, and he believed that with these laws we tend to learn. Okay, so these are all part of like how we think. So now the question is, where are these associations stored? So in the previous slide we saw that we learn because of the associations, and how associations are formed. Let us say because of the Aristotle's 4 laws of association: law of contiguity, frequency, similarity, contrast. Okay. So we learn because of the associations we make. Okay, that's fine. But the question is, where are these associations stored or processed? Okay, so far what Aristotle said is the law of how we may be associating things, but who is associating this? Where the association is happening? Okay, in the computer we say that computer is running some code, but we know the logical unit of the computers, the registers, the cache, and all this are involved. Okay, and we know the correct mechanism also. So how things get logically converted to bitwise operations and so on. But for the human beings, we ask the same question. Okay, so how do we process things, right? Because that is important, right? So Feynman, remember what he said: if you can't create, you don't understand. Okay, so if I cannot create a way of learning, perhaps I don't know also how learning happens. Okay, so just coming up with theory is not enough. We need to build something that actually can do those associations on its own. So there was a theory that was proposed. It's called connectionism. Okay, so connectionism is another. So what connectionism theory says is that the associations that we have, the Aristotle's law of association doesn't get violated anyway, because what he said is actually correct. Okay, that is how we do remember. If we see things multiple times, we do tend to remember. If we see things, similar things, we remember. Contrasting things, we remember, and so on. So the point here is like how actually these associations are made or processed. So that's the major question. So to answer this, the theory that came was something called connectionism. Okay, so how connectionism, the idea behind connectionism is they had some idea of initial structure of the brain, and they saw something like this in the figure. You have some node like graphical structure kind of thing, and you have nodes with this star like things, lights coming out, and then you have connections between them. Okay, so brain seems to be like mass of interconnected neuron, and it is believed that the brain is doing all the processing. So in more detail, it looks something like this. So there are these cells, and then so-called neurons, and then they are connected with synapses and so on. Okay, so many neurons connect to into each neurons. Okay, so the proposal was from the report Mind and Body in 1873 that the information is stored, or information about the associations is stored in these connections. Okay, so the claim is that the storage is in these connections itself, or the edges that you see here. Okay, between the neurons and so on. Okay, so again, this is a very vague theory, like it's stored in connections, but again, we don't know precisely like what is going on. Okay, so how, right? So so neurons connected to other neurons, that's related to the brain, and the processing capacity of the brain is a function of these connections. So again, these are the statements that were made, and again, these are philosophical right now. So connectionist machines emulate this structure. Okay, so if we are going to build a machine, then it has to be to follow such kind of structure. Network of processing elements. So this is considered to be a network of processing elements. Okay, all world knowledge is stored in the connection between the elements. Okay, so that's the claim. Like everything that we know, obviously all world knowledge, because all world knowledge is a cumulative knowledge of all the human beings. Okay, in particular, let us say brain. And if we take a union of all this, then all the world knowledge is lying there, because I don't think other species have those knowledge. Okay, or they may not be aware of, maybe. Okay, not at the scale that human beings are. Okay, so graphically this may look like this. Okay, so here this is how we may see the neurons and then the connections between them. So the neural networks are connectionist machines. Okay, so these are the new keywords that we are using, as opposed to the von Neumann machines. The von Neumann machines that we see in our PC and yeah, even even the mobiles are not exactly the original von Neumann, but they are very close. Okay? They also have some kind of a cache and register model and so on. So somewhat they are all related to one, unless you start working with the general architectures. If you are an electronics guy, then you might know those generic architectures that people build. Okay, so those field programmable gate arrays, and then you can actually rearrange things on your own. Okay, so there may not be concept of the memory hierarchy and so on that we are more familiar with in the von Neumann architecture. Those are the key things, right? So so von Neumann architectures are the ones that we have in the laptops and the computers and so on and so on. So so these are the more familiar ones. So this is how the von Neumann architecture looks like. You have a processing unit, you have a memory. Here the memory itself has a lot of hierarchy. Okay, RAM, cache, many layers of cache, and then registers. Okay, and then so the program that I write, okay, it's executed, it goes to the RAM, and then RAM passes it to the cache, and then cache goes into the registers. And in the registers, I have like floating point units and so on, and then the calculations are done, and then it passed back, and then that's how we retrieve our result. So this is the classic von Neumann architecture. And then if I have a multiple processors, then I will talk to them via network. Okay, so there is another processor here, and then I can talk to them via, let us say, some kind of message passing. Okay, or any other communication protocol. Okay, over Ethernet, or even more efficient like InfiniBand and so on. So these are the usual way we see things, right? So this is our computing machines, and we are trying to relate it to connectionist machines that is inspired from the brain. Okay. So the memory has many nonlinear processing units. The program is in the connection. So we are talking about connectionist machines, which we believe it has many nonlinear processing units, and the program is in the connections between these units. And the program is somewhat stored in these connections. That's what we are claiming. Okay, so these connections are storing the program. In this case, our program is stored in our disk, right? So our program is stored in the disk. Okay, and from disk it goes to the RAM and so on, right? So we have explicit idea of where the storage is of our program, but in these cases we are claiming that they are stored in these edges between the neurons. Okay, so that's the claim. Okay, so the basic model was again like divided into two parts, A-type machines. So it could be seen as a network of NAND gates. So remember that NAND gate is a fully complete. Okay, in the sense that it can generate any logical operations that you can think of. It can generate AND, or, okay, NOT, and so on. And we know that AND and NOT are fully complete. Okay, functionally complete set of operator, meaning that it can generate any set of logical operations. So just one set of NAND gates is enough for you, although it may get complicated to just use NAND gate only. But nevertheless, we believe that if we could generate any kind of logical unit, and we need a NAND gate for that, and connectionist model, we can think of these as a B-type machines proposed in 1948, and the connection between two units has a modifier. If the green light is on, the signal says through. If the red light is on, the output is fixed to 1. The figuring out how to manage the colored wires. Okay, so let us look into this. Yeah, so and yeah, so before coming to these B-type machines, okay, let us continue with this. So one of the other questions that people ask were, are we a giant parallel distributed machine, and what are the components of machine? So one idea here was that we have many parallel computing units, okay, and then they can process it independently, okay, and then they can communicate with each other via some connections, and then they can they can give a cumulative result. Okay, so one other proposal that came was a parallel distributed machine, So what are the components of this model? In this case, we have set of processing units, set of activations, output function for each unit, a pattern of connectivity among units, and propagation rule for propagating pattern of activities through the network. Okay, so an activation rule for combining inputs impinging on unit with current state of that unit to produce new level of activation for that unit. So this is another set of model that was proposed, where the idea is to use several processing units and so-called activations and so on, and then there is so-called propagation rule and so on. Okay, so that's one. Okay, so I'm going to skip a little bit. So the idea here is to get inspired from the brain, and so this is the typical picture of a neuron. So we have so-called dendrites, and then so-called soma, the main part, and then the axons. Okay, so it's indicated by this arrow. So signals come in through the dendrites into the soma. As a signal goes out via the axon to other neuron. Only one axon per neuron. Neurons. Okay, one more interesting thing to note here is that neurons never undergo cell division. So have you wondered why? Okay, neurons never undergo cell division. So once you have the neurons, they are there. Okay, I mean they will never go cell division like other parts of the cell in our body. Okay, so and the neurogenesis occur from the neuronal stem cells. Okay, and it's almost stops after the birth. Okay. Okay, so let us go and build the synaptic model. So synaptic model will look like this: transmits weighted input to the neuron. Okay, so this is an excitatory synapse, and then there is so-called inhibitory synapse. This is the excitatory synapse, and this is inhibitory synapse. So any signal from an inhibitory synapse prevents neuron from firing. Okay, so any signal that comes via this, it will stop the neuron from firing or processing. Here the firing means processing, and excitatory synapse will allow the neuron to actually transmit the weighted input. Okay, so both have like opposite function here. So the activity of an inhibitory synapse absolutely prevents the excitation of the neuron at that time, regardless of the other inputs. So as long as the moment you have inhibitory synapse going in, then you're sure the neuron is not going to process any incoming signal. Okay, so the activity of the neuron is an all or none process. Okay, according to the synaptic model, a certain fixed number of synapses must be excited within the period of latent addition in order to excite a neuron at any time, and this number is independent of the previous activity and position of the neuron. Okay, the only significant delay with the nervous system is the synaptic delay, and the activity of any inhibitory synapse absolutely prevents it. This is the same thing that we discussed here. So any signal that comes in from inhibitory will stop it. Now, what is the signal strength and how they will be processed? That's okay, different story. But we are at a very top level modeling here, where we have these two things: excitatory synapse and inhibitory synapse. And the structure of the net doesn't change with time. So these were all the models. Okay, we don't have to go into too much detail of these initial models, but just we are doing some quick review. Okay, so even if you don't get a full idea, don't worry about that. Okay, so these were the initial things, and the neural networks can perform Boolean operations with this synaptic model. Then later the claim was made, and then a proposal was made of McCulloch and Pitt's net. Okay, so they proposed this synaptic based model, and based on that they could do some logical operations. Okay, so for instance, they can do the disjunction. Okay, so disjunction, and it's like the OR operation they can do. So this is the OR operator, and they can do the AND operation. Okay, for the conjunction is also called AND operation. So they can do OR operation, they can do AND operation, they can do NOT operation. Okay, they can model this. Exactly details we don't want to go into this. Okay, so this was the contribution of the synaptic model. So they can even create an illusion of perception. So with the synaptic model, we may build a sensor that can be that can tell us whether it's heat or cold and so on. Okay, so we are again not going into too much detail of this, but they showed that these kind of nets are able to do that. Okay, so the claims of synaptic model was that the net should be able to compute small class of functions, claim that the net can compute a richer class of function if the tape is provided. By tape here means the memory. Okay, so what they seem that they are lagging behind in their model is to somehow incorporate the memory also, because memory is also needed for temporary assignments and so on. So they believe that for bigger computations, they need a memory. Additionally, they will be equivalent to Turing machines. Dubious claims that were made that they are Turing complete. They didn't prove any results themselves, didn't provide a learning mechanism, and so on. So these were like the disadvantages of this model. And then came the Habian learning by Donald Have, and according to him, when an axon of a cell is near enough to excite a cell B and repeatedly or persistently takes part in the firing it, some growth process or metabolic change take place in one or both cells such that A's efficiency as one of the cells firing B is increased. Okay, so what in this Habian learning, what is different now being proposed is that it's taking care of the of a repetitive effect. Okay, so if things remember law of Aristotle said that law of frequency is there, right? So law of frequency suggested that if things happen frequently, okay, very often, then also the associations are strong and we'll tend to learn. So this is what is being incorporated by Donald Have via this so-called after his name, it's called Habian learning, and it tries to incorporate that. It says that learning should get strengthened if the excitement happens repeatedly and persistently. Okay, so that's the yeah. So that's the claim that. So if it's not get excited more and more, if it is not getting excited repeatedly more and more, it will learn less. Okay, about that. Okay, so there is something called like so here like you tend to see in the modern day learning, you see the effect of data. Okay, so more and more data is better, right? Because you will repeatedly feed into the network, and the network will become better and better in learning. Okay, so this is where like you get a sense of supervised learning and how more and more data is better. Okay, so as A repeatedly excites B, its ability to excite B improves. Okay, the neurons that fire together wire together. Okay, so that's a very famous word. Fire together are also wired together. So if the neurons with certain signal they are firing together, then they will have stronger connections between them. Okay, so these are the proposals here. Okay, so in the Habian learning model, we have some like top level view, but from the maths point of view, what we have is like if neuron xi repeatedly triggers a neuron, the synaptic knob connecting xi connecting to xi gets larger. Okay, so and if we try to write down the mathematical model of the Habian learning, then we believe that there will be some kind of weight in the network, and this weight gets updated like this: the old weight plus eta times xi and y. Okay, so details are not so important here. Okay, why what exactly are these y and xi and so on, but there is some kind of a gradient descent being done here. Okay, to update the weights of the model. And remember, in the gradient descent, more you have the data, okay, the more your weights will get strengthened, because more the weights will get tuned, okay, in a better way. Okay, so the simple formula is actually the basis of many learning algorithms in machine learning. Okay, The issues with Habian learning is stronger connections will enforce themselves, no notion of competitions, okay, and no reduction in weights. Learning is unbounded. Generalized Habian learning is then proposed, where the updates look like this. Okay, so again, we are not going into too much detail of why they proposed like this. Okay, the contribution of an input is incrementally distributed over the multiple outputs in this case. Okay. There is an improvement over the Habian learning by something called Perceptron. So this is where like we want to focus on Perceptron. This is the basis of initially I talked about basis of what the neural network. These are the Perceptron, and they proposed something like this. And you can see that if you have seen a neural network by now in the other classes like SMAI and so on, you know by now like how. I mean, this is very similar to the neural network, right? So this is the retina. Okay, so retina is, and then there are like layers, and then yeah, so these are these are the different layers. Okay, and then you have the weights between these neurons between the layers. Okay, so this is what was proposed. Okay, so the groups of sensors on retina combine onto cells in association area A1. Okay, so this is the association area A1. Groups of A1 cells combine into association cells A2. So this is A2, and signals from A11 cells combine into response cells. Okay, and so A2 cells again they combine into the response cells. All connections may be excitatory or inhibitory. Because obviously, like some connections may be excitatory. So in other words, like maybe higher weight, and some connections may have very lower weight. So it will correspond to like not firing at all. Okay. So even included a feedback between A and R cells. Okay. So this is like the so the modern way of saying the feedback. I mean no. I mean the feedback means here also the backward. Backward loop is there. Okay, so there are some arrows that are going backward like this. Okay, and there are arrows that are going forward. So even include the feedback. So where does the feedback is needed in the modern day RNNs, right? RNN has this feedback loop, right? So recurrent neural networks, you go back, right? So that's there is a feedback loop. So recurrent neural networks, if you see there is an input, okay, and there is an output sequence, X1, and then Y1. And then in the next time step, we go there, you have X2, but then Y1 is also now taken as an input for the next time step. So that's why it's called feedback, because the output is now fed back to the input again to the same network. This is just different timestamp, but it's basically the same network. So this idea of the feedback, actually it's related to now RNN. So even that is something they already thought about this, okay, a long time ago, that it may be essential also to feedback. So which networks today have feedback loops? Well, these are RNN, like I said. Okay, so let us get into quickly into the perceptron. Okay, so we have skipped a little bit of detail in the previous synaptic model and so on, because we wanted to get to the perceptron. So let us see what are the modern definition of perceptron. In perceptron, you have the inputs and then you have the weights, like we have shown the edges and then neurons and so on, right? So, and then there are symbols here, and then there are some something here. I see threshold and something, and then output is there. Okay, so we will try to see what this means. So number of inputs combine linearly. So these are the inputs. I have n inputs. They will combine linearly. So remember from linear algebra, what is the meaning of linear combination? So linear combination would mean W1 x1 plus W2 x2 plus dot 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 plus Wn xn, right? So that's what we did. We combine linearly. So that's what this sum means basically. So sum operation is equivalent to saying that we combine linearly. Okay. Now threshold logic. is there. So that's, we see threshold is here. Fire if the combined input exceeds threshold. So this threshold unit will fire if the combined unit exceeds threshold. Okay. So we can define some threshold like this, where y will be 1 if the linear combination minus some threshold t is greater than 0. So if the linear combination of this guy exceeds certain threshold, then we will classify it as 1. Otherwise, we will classify the output as 0. Here t is some threshold. Okay. The originally assumed could represent any Boolean circuit and perform any logical operation. So this is about this perceptron. So perceptron can perform any logical unit. So far, we don't know how it can perform. So for example, can it do and so on? So we will try to see, right? So if I pass 1, 0, and this is my perceptron, let us say P. So can it do the AND operation? Okay, so can it do the AND operation in this case? Okay, so can it do AND operation and so on? So or the OR operation, NOT operation. Okay, so this is what is being claimed here, and they actually proved that they can do this. And in fact, we can also try to prove that. Okay, in a while. Okay, so this was the big news, and then quickly some claims were made that it's an embryo of an electronic computer that expects will be able to walk, talk, see, write, reproduce itself, and be conscious of existence. So that was the New York Times of 1958, and when the perceptron was proposed, and so they already made a claim that this is so powerful that they will be able to walk, talk, see, and so on. To some extent, this is right in today's environment, because we do see that neural network, for the moment, it's able to talk, is able to see, in the sense that it can recognize objects. Okay, so this is something we know by now. It does. It can recognize objects. It can write also now. Okay, so it can actually write some. It is able to now generate text and so on. So it is possible to write and so on. Maybe walk and all this is still a work in progress. Okay, so that's maybe for the robotics guy to figure this out, how to make a robot walk using the neural networks and so on. Yeah, so it can talk, obviously. So these were the claims, and it seems like to a large extent it's correct now. Okay, so but then there were other papers that said, okay, it's a Frankenstein monster designed to by Navy that thinks. The Frankenstein, if you recall, the meaning of Frankenstein is like a creator who destroys a object that destroys its creator. Okay, so that's called Frankenstein. So it's like is it that this will destroy human beings also, right? Okay, so the Percentron learning algorithm looks like this. It's very similar to the gradient update. D is the desired output in response to the input X. So this is my desired output. I take a difference from the expected output. Okay, so the Y is the expected output, actual output. And yeah, the question is this the gradient descent? Well, it is very similar to now gradient descent, right? So gradient descent would look very similar. Okay, in this case, like, it's a good exercise for you to figure out what could have been the loss function. Okay, based on which they proposed this. Okay, it's a good exercise to figure out. But yeah, so we can see this as a special case of gradient descent with some special loss function. Okay, so features, what are the features? Only Boolean task it can do. So far the initial perceptron was only good for Boolean task. Updates the weight whenever the perceptron output is wrong. How it will update the weight? Using this perceptron algorithm. Okay, so let us see whether it can do the AND operation, right? So can we build a perceptron? So it seems like we can build, because I mean, what are the things that we need in our model, right? So we need the weights, and we need the threshold T, right? So if you want to do the AND operation, then I will build this perceptron. If you want to do the NOT operation, I will build this perceptron. If you want to do the OR operation, I will build the OR operation. So you can think of this as AND gate, NOT gate, and OR gate, right? So you can think like this. So will it do? Will this work, right? So let us say I pass X and Y as 1, 0, right? So I pass 1, 0. OK, and this is our network, right? And this is our threshold. So let us do the calculation, right? So linear combination, right? So 1 times 1 plus 0 times 1. So this is 1. OK, so 1 is greater than 2. No, right? So 1 is greater than 2. It's no. Greater than 2. No. So the output will be 0. OK, so 1, 0. The output is 0. So similarly, we can try, let us say 1, 1. So 1, 1, and then 2. So this model is like already learned for us. So now we fix. So linear combination is 1 times 1 plus 1 times 1 is 2. 2 is greater than 2. OK, so what? I think equal should. Yeah. So in the threshold, I think we will allow the equal, and then otherwise it's 0, right? This was no, but this is like equal is yes, right? So this is yes. So this implies that the output will be 1. OK, so the output will be 1. OK, so this is how you can also verify the other cases. With this threshold, it will act like an OR, it will act like an AND, it will act like a NOT. OK, so you can verify this yourself. So this does work like a Boolean gate. But the question is, some people asked, can it learn a XOR operation? OK, the exclusive OR. So can it learn exclusive OR? It turns out that any of these cannot, like I cannot build a perceptron with this any value of t and then any value on the weight such that I can get a exclusive OR. Remember that these are binary operations, so I will have only 2 edges, right? So I'm looking for only network like this because perceptron looks like this. It has inputs. So for the XOR I need 2 inputs, and then I need edge weight. So there are 2 threshold. So you cannot guess the weights and then the threshold such that it will work like a XOR. OK, exclusive OR. So the people said that although perceptron is good at I can do AND and OR and NOT, but it's not able to produce XOR operation. OK, so the perceptron doesn't seem to be that general. OK, so well, the answer to this is like maybe only single perceptron is not able to learn. But what if I'm allowed to combine perceptron? Can I not implement XOR? So this was the counterexample given by Minsky and Peppert in 1968, claiming that the XOR operation is not really possible. OK, with only one perceptron. OK, so unfortunately it cannot learn XOR. The idea, as I said, just I gave a hint. Maybe you need to combine several perceptron. OK, so the question is single neuron enough? Individual elements are actually turning out to be a weak computational element. So Marvin and Minsky papered 1969. So that introduction to computational geometry. OK, so that's where they propose this idea that the XOR operation cannot be done and so on. So what we need is network of perceptron basically. OK, so something like this. So if I was given 3 perceptron, so each corresponds to 1 perceptron, right? So I have 3 perceptron, then I'm able to learn XOR. And the example how we can build is exactly given here. You choose this threshold 1, 1, and then you will get this. So we can play with this. Let us say we start with 1, 1. So let us say 1 and 1 is here, right? So I take a linear combination of these, right? So to get here, I need a linear combination of 1 times 1 plus 1 times 1 and then plus one more edge is coming here, right? So it's 1 times the weight is 1 times 1. So it's like 2 here. So 2 is here, right? And here I have to compute. Okay, so 1 times -1 is -1. Okay, and then 1 times -1 is -1. Okay, so -1 plus -1 is -2. Okay, now the question is 2 greater than the threshold? No. Okay, so the output will be 0 here. So the actual output will be after the activation will be 0. And here is -2. I mean, sorry. So is 2 greater than 1? The answer is yes, right? So since the answer is yes, so I need to like, okay. The answer is 1 here. Okay. Yeah, so 2 greater than 1. -2 is not greater than 1. So answer is 0 here. And 1 times 1 is 1. And 0 times 1 is 1. So total is 1. So 1 is greater than 2. No. So the output is 0. Okay. So 1 exclusive 1 way is 0. Okay. So that way, like it, you can check all other inputs, and it will work like a XOR. Okay. So the idea here was that use multiple perceptron if you want to emulate some other logical operations. So from here, the idea of multi-layer models came, where we can think about multiple layers in our model, like in this case. So we will have a set of inputs. Now we are plotting perceptron in this direction. So inputs are here, they go in, and there are 4 perceptron in the first input layer, first layer, hidden layer, and then the 2 in the second. And then lastly, we have 1, and that gives us the output. Okay. So that's where the idea of multi-layer perceptron model came. So it can compose arbitrarily complicated Boolean functions. In cognitive terms, can compute Boolean functions over sensory input. Okay. Okay. And now the second challenge is like going from Boolean to real. Okay. So far we were working with Boolean. So it can do Boolean logical operations on the Boolean. Now we are thinking, what if we extend this to real? If we look into the humans, then we are an kind of analog machines. Okay, so there is a certain amount of voltage and so on, and these are like continuous quantities. Okay, these are not not like digital. Okay, so it could take any continuous value. So 0.3 could be a voltage, 0.32 is a voltage, and so on, right? So these are based on analog inputs. In other words, like it can take any real number, right? So what makes the non-Boolean inference and predictions, or we make non-Boolean inference and predictions? We believe that not really. Okay, so we believe that we have a very good sense of continuity, in the sense like we can sense a very varying degree of feeling of, let us say, heatness, brightness, and so on. Okay, so it's like we can process data with real numbers. Okay, not just Booleans. So we can, why not also allow for the real inputs, real numbers, not just Booleans. And also we allow our weights to be real valued, and output we may still keep it Boolean for the moment. In other words, the output could still relate to the classes. Okay, so 0 or 1 class. Okay, so a more concrete model of a perceptron will be this, where the input is allowed to be real, weights are allowed to be real. This is as usual the linear combinations, and then we have some threshold. So now our threshold function t is now replaced by some other kind of threshold. It's so-called sigmoid. Okay, so it's so-called sigmoid. So the sigmoid function is like exponential of the argument. Okay, so e to the 1 by 1 plus e to the argument that you have here. Okay, so it is sometimes called like z. So this is equal to 1 by 1 plus e to the minus z, right? So this is how the Sigmoid function will be defined here. Any real valued activation function may operate on the weighted sum. So this is our activation function, and this can now act on some real data, okay? Because weights are now allowed to be real, xis are allowed to be real, bias are allowed to be real. So now it can operate on any weighted sum. The perceptron maps real valued inputs to real valued output. Obviously, for the moment, assume the Boolean output y as follows. So the output that we define, so this is one way to decide the output, and we can also define output via our original threshold technique. So we can set some value t, and then we will say whenever the linear combination is greater than that threshold value, it will be 1, otherwise it's 0. Okay, so in terms of figure, then what we see is like w1 x1 plus w2 x2 equals to t will be the equation of a line. Okay, in this case, this is the hyperplane you can think of. So if the values are like greater, then it will be this side. So this is like w transpose x is greater than t, then this class is class 1, and if w transpose x is less than equal to t, then this is class 2. Okay, or you can take this and okay, so greater than equal to is defined like this, and then the strictly less is this class, right? So this is so what is happening here is that perceptron in some sense is like a linear, especially this model. This model is like a linear classifier. Okay, so just like in the SVM we saw, in SVM we were also looking for a hyperplane that can separate the two classes. So this were the 0 class here, and this were the other classes here that we are thinking of, and we are looking for a hyperplane that can separate the two classes. So here we are not talking about any margin or anything. In SVM we were also talking about margin, right? We were taking some supporting hyperplane like here and here. So these were the support vectors and these were the support vector, and then we were trying to maximize the margin. That we are not asking in the perceptron. Okay, those constraints are not here. Here we are saying, okay, find one hyperplane, and then if you are on that side, then you classify 1. If you are on the other side, you classify class 0. Okay, so this is the geometrical intuition behind the perceptron, and we can explain this also in the 3D case where we may want to classify, where we will also have an hyperplane. Okay. Okay, so once we know that perceptron, a single perceptron is like one classifier, in other words, one linear classifier, so it can find one decision boundary. So then the question is like, can we use those perceptrons to learn complicated boundary? In other words, can I build a perceptron that can identify that this dot here, okay, is inside or outside? Okay, so can it learn that? Can a perceptron be built such that it will tell whether the point is in the yellow shaded region or not? Okay, so what could be our intuition, right? So our intuition here is like perceptron we know can learn. So this is like a polygon shape, right? So polygon is a union of, like, it is made from the boundaries, and these boundaries are nothing but the planes that we are looking for. So we know that perceptron is good in learning the linear boundary. So what we know is like this is one plane. Okay, and so I mean I have just extended this, and this is like another plane. I have just extended this. I have just extended this, and I have extended this. I have extended this. I have extended this. I have extended this. So these are the planes actually we are looking for, because this plane will tell me. So this perceptron will classify whether the point is this side or this side. Okay, so this will at least tell me whether it's this side or this side. Okay, so if I'm focusing on this point, then this perceptron will tell me whether it's this side or this side. So it is on this side. OK, so this tick is done. Now this perceptron will tell me whether the point is on this side or this side. So again, this is on this side. OK, so this perceptron gave the value 1. This perceptron gave the value 1. This perceptron is also giving the value 1 because the point is on this side of the perceptron. The point is again on this side of the perceptron. So there are 5 1s. OK, so there are 5 1s. So if there are 5 1s, in other words, the point is on this side of this side hyperplane and this side and so on, then I know that the point is in the yellow shaded region. So that's the idea behind how I can build a perceptron to know that the point is inside the yellow region. OK, so that's the idea. So in other words, how many perceptrons I need? 1, 2, 3, 4, 5. I need 5 perceptrons. OK, so I need 5 perceptrons, right? And what do I need? So each perceptron, so 2, 3, 4, 5, right? Each perceptron will tell me. So the point X goes to each of these. OK, the point X goes to each of these. Each of these tells me whether they are on the correct side of that. OK, so correct side of that, and then there will be a final perceptron that will check the threshold. So threshold, what is the suitable threshold here? Threshold is like 5, right? OK, so this is what we are planning, right? So given a problem like this, I figured out I need a 5 perceptron to learn each of the boundary, and then obviously I have to train my model, right? So these are the weights W1, W2, W3, W4, W5. And I have many points like this, and also I will have points that are outside. And for corresponding those points, I have the labels that, OK, when it's inside, I will flag that it is a correct answer, and then if it's on outside, it will flag it as wrong, as 0, right? So this is what like I'm planning, right? This is the template of how I'm going to model this problem. OK, so this is what I said. The first perceptron will take the input x1, x2, and it should produce an output. The second perceptron is the second boundary it's learning, third boundary, fourth perceptron, and then fifth on also. OK, I have not shown all. There are 5 boundaries. So each neuron has a decision boundary. They fire when the input is on their part of the hyperplane. OK, assuming that they fire S1 above, how do we get the final fired exactly when the input is inside the polygon? Well, this is the final picture. So I have x1 and x2, and they are going to all the input, and then from there we will check whether the output sum is greater than the threshold, which I need 5. OK, so if they are greater than 5, equal to 5, then I will flag that OK, the point is inside. OK, so the final neuron does the sum, and if the input is the intersection of all the half spaces, and that will mean that sum of yi must be 5. Then the sum is 5, then the given sample is inside the pentagon. OK, so this is how we do this. So we can also learn complicated boundaries like this. So in this case, in this case, what do I observe? I observe that there are like 2 pentagons, and I see that they are so each pentagon will have 5 lines. So I will need a 5 perceptron for each. So for one pentagon like this, I will choose this, and for another perceptron like this, I will choose this set of perceptrons. So these are the first 5. These are the second 5. OK, so they are learning the first perceptron. So learn first pentagon, and these guys are learn second pentagon. OK, so individually they can learn, and then the question is like the point is on either of these, like either. So to find that the point is on either, I will do a final OR here. Here I do an AND to make sure that this is inside the pentagon or outside the pentagon, right? So this is locally it's saying whether it's inside or outside. The outside could be also inside this guy, right? But this is only telling whether it's inside or outside, and this AND is also checking whether the point is inside or outside. But that outside could also be here. right? So to make sure that it's in either, then finally we do an OR of this guy. Okay, so if we do an OR of this guy, then we get to know whether the point was in either of these. So this will make sure the point was inside. This will make sure the point was inside or outside. OK, if it was inside also, the OR will be true. If it was only here, then also the OR will be true, meaning that it's in this one. And of course, if both, I mean, OK, in this case, it cannot be in both. A point could be in either this or this, right? Yeah, so it cannot be in both anyway. OK. OK, both will be very interesting, right? So because there will be a intersection here, right? So it will be interesting to see how perceptron will behave in that case, right? OK. So this is how it looks like, and we can build some more complicated neural network that can learn maybe a point inside this complicated object. OK, so the point that is lying inside, right? So it's just that now the work is a little bit more, because I will try to approximate these lines, right? So this body by series of lines, right? So I will have so many lines, right? And then for so many lines, I will need so many perceptron, and then I can identify. Similarly, I can try to approximate a horse and so on. OK, so the basic idea can be extended to learn many things. The only problem is, like, for a more complicated objects like this, you need to have lot more finer approximation by lines, and hence you will end up using lot more perceptrons. But we will see. Well, I don't know if we will see or not, but but there are like other ways to deal with image, like image recognition and so on, the so-called CNN, right? So we don't go via this route. OK, so we use the concept of filters and so on in CNN. OK, but from here we get an intuition of what could be, why perceptrons are indeed powerful. OK, so more complex decision boundaries can be composed. OK, so we approximate them by small polygons and so on. So this is an example of a hand digit recognition. So here you can see an image pixels. OK, so image for us is a pixel, so set of pixels, and it's looking like a number 2. OK, so so it will be fed into the so-called neural networks. It's a multi-layer, or you can think of this as multi-layer perceptron. And then it will be trained over that. OK, so and then a check will be done whether it's, because a training will be done on the label data. So if I already know that, let us say it's 2, so I will keep feeding, and then I will check with the output, and then based on that I will update the weights and so on. So find decision boundaries in higher dimensional spaces. In higher dimensional spaces, we are supposed to find decision boundaries. So in that case, yeah, we let the neural network do all these complicated tasks. So to come back to our previous problem, what is there in these black boxes? That something goes in, voice signal goes in, transcription comes out, images goes in, and text caption comes out. Game state goes in, and next move comes out. Voice signal goes in, and transcription comes out, and so on. So what do we put in these black boxes? They are now somewhat clear to us. These are nothing but neural networks. OK. So behind all these black boxes are nothing but neural networks. Neural networks are multi-layer perceptrons, you can think of, with neural networks being like incorporating many things there. OK, so in general, it's like a lot more things have been included in neural network now from the basic multi-layer perceptron idea. OK, so we have seen that we were talking about threshold, because so it seems like threshold is also an important aspect. So we can like talk about various kind of thresholds, such as sigmoid and 10H and so on. OK, so we will talk about these in detail a bit later. So what we understand is that we do a linear combination, and then we do activations, and then this after activations we, yeah, so that those are activation functions are given by there are some templates for activation functions which are listed here, and also rectified linear units and so on. So ReLU and so on. So I will point out this precisely later on. So there are various types of activation functions also. Okay. So MLP with a sigmoid activation function. So if we look into the sigmoid, so sigmoid was, what was that? 1 plus e to the minus z. Okay. So this was the sigmoid function, if you think of. Then for these, what we do first is like we take a linear combination, and then we may compute. So one goal for us is to compute the derivative with respect to the weights, right? Why do we want to compute derivative with respect to the weights? Because we want to use that in the gradient descent, right? So to do that, we can use a so-called chain rule. Okay. So y is a function of z, and z is a function of w. Okay. And w is a function of x, obviously. So if we have to compute the derivative with respect to wi, we can use the chain rule, because y is a function of z and z is a function of w, and then dy by dz we can substitute it by sigma prime z. Okay, so this is the sigma z, and then yeah, so dy by dz will be sigma prime z, and then dz by dwi. If I take derivative of dz with dwi, I will be left with xi. Okay, the partial derivative, right? So that's why you have an xi here. Okay, and similarly, I can also compute derivative with respect to xi. So for activation functions like sigmoid, it is a differentiable function, because 1 by 1 plus e to the minus z is a differentiable function. Exponential is a differentiable function. So that's a good thing. We can differentiate and compute the gradients. This means that we can compute the change in the output for small changes in either the input weights. Okay. So the whole idea behind computing gradient is to understand the sensitivity with the input. Okay, and this sensitivity is what is the gradient of the loss that we use in the gradient descent, right? And these sensitivities are these nothing but the derivatives here. Okay, and we tweak this in the gradient descent to optimize the weights here. Okay, so so if the activation functions are differentiable, then we get so-called differentiable networks. Okay, so and then in this example we can write like this. So the final step will be sigma of so this is like W11 weight, and then this is like W21 weight, and then we can add the additional weight as a bias. Okay, so bias is also a weight. Okay, so that is feed in, and then we took a sigma here. So we take a linear combination here, and then sigma, and then this is the output that we get. So in general, this is how at each layer the output is. Okay, so y here is the overall network output. So that's the final output. Wki is the weight connecting the ith unit of the kth layer to the jth unit of the k plus 1th layer. Okay, so this is like a mouthful, but you get the idea of what it means. So it's 1 to 1. Okay, and this is like the second neuron connecting to the first neuron, okay, of the next layer. So these are just the notations, and yki is the output of the ith unit of the kth layer. Okay, so similarly, like here, this is the output of the first unit. So these red things are also called units. Okay, so units. So this is the output of the first unit of the second layer. Okay, so this is the first layer, and this is the second layer. Okay, so the first unit of the second layer, second unit of the second layer. Okay, so these are the notations you should be familiar with. And if we choose the sigmoid, then it's differentiable with respect to both w and y. Okay, so what is the optimization model for the neural network? Well, optimization model for the neural network is like I will pass in various samples, and then I will define a loss function. So this f behaves like a neural network for me. So f xi W is the neural network function. Is the neural network function. Okay, so if we pass in xi, so this takes in xi as an input, and weights are there. Of course, you are learning the weight during the gradient descent. Okay, so it depends which. It's a function of what. It depends on whether you're doing training or testing, right? So during training, f is a function of which one? Okay, during training, how do I see this? I see this as a function of W. Okay, and during testing, f is a function of x. Okay, because W has been learned. Okay, so these are the things we remember. During training, f is seen as a function of W, and x are the samples that we are given already. So these are known, and W is something we are trying to figure out. And we can define some loss function, and yi is the given set of levels we are known to us. So we can define some suitable loss function. So what is the difference between the neural network output and the actual output? And we will take some kind of a measure of the difference, and that's how we define the loss function. And obviously we need to minimize the loss function. Okay, so on the outset, this is what the optimization model is. It's unconstrained optimization problem. And depending on the, well, not depending, but actually the loss function usually will be non-convex now. Okay, why it will be non-convex? Because you are talking about functions like this. Okay, so functions like this will look like how? 1 by 1 plus e to the minus w1 x1. Let us say just two variable w2 x2. Okay, so is this a convex? Not really. Okay, so this is not convex. In fact, it looks something like this. Okay, so it looks something like this, and certainly it's not convex because the line joining this guy is below the graph. Okay, so sigmoid itself is not convex. So here the f guy is like that sigmoid of some z or something, right? So this is not a convex function itself. Okay, so convex function minus yi. Let us say I take the loss to be just minus and then square it. Let us say the squared loss. Since this is not convex, there is no guarantee that the overall thing will be convex now. So we already see that it's a non-convex problem. And also we observed that it's unconstrained. We did not have any constraint on W weights. Okay, so it's an unconstrained optimization problem, but it's a non-convex also. So neural networks are a rich set of examples of non-convex. To solve this, we will use gradient descent. So now we know, right? So this is like minimum of LW function, and W is unconstrained. In other words, W is in Rn, like anything. Okay, so this is an unconstrained optimization problem. Unconstrained. Okay, but non-convex. And we know how to solve problems like this. We know in the sense like one of the simplest way is gradient descent we can try. Okay, we will learn also other variants, but one variant we know is so-called gradient descent. So these are the models for the neural network, and f here obviously is the nested function of weights. Okay, so this is how we can apply the gradient descent for training in a neural network. Okay, and what I am going to describe is something called stochastic gradient descent. So what we have seen so far is a gradient descent, but there is something called stochastic gradient descent. So let us see what is that. The stochastic gradient descent proceeds as follows: set a learning rate epsilon and an initial parameter setting theta. So theta are the weights here. Okay, so these are the weights. I am using sometimes theta and sometimes W. Set a mini batch size of m examples until the stopping criteria is met. So now you are setting a mini batch size of m samples. Okay, mini batch size of m samples until the stopping criteria. So sample m examples from the training set and their corresponding outputs. Okay, So you have like many samples, but then from there you will take only m of them. Okay, you will take only m of them and then the corresponding levels, and then you will compute a gradient only on those m of them. Okay, so remember what is the full gradient? Full gradient. So the loss function. First step is the loss function, right? So if you go back to the loss function, right? So this is like sum over all the samples I did, right? Because I'm putting in xi and then I'm checking whether it's matching with yi or not, right? So let us say I have I equal to 1 to m. Okay, I think this m and the other m will contradict, I think. Okay, so let us say this is n. Okay, so I equal 1 to n. So I have samples like this x1 and then the corresponding level y1, and then I have x2 and then corresponding level y2, and then I have xm, sorry, n, and then the corresponding level yn, right? So the loss will be defined for each of these, right? So what is the difference if I put the xi in the neural network and then the output I get will be f xiw, and then I take a difference from yi and I sum over these all. So that will be this sum over 1 to a capital N. Okay, so uh, so so this will be the full loss function that I'm thinking of, right? So if I take a gradient of the loss function, then it will be sum of the gradients of the individual terms, right? So this will be sum of the gradient of the small l, okay, f xi w yi, right? So this will be the sum over I equal 1 to n. So remember what is happening here? Here I'm summing over all the sample, right? The stochastic gradient method says that you only take sum of these, sum, not SUM, but SOME, sum of these samples, and then you only sum over this sum samples, right? So let us say I choose M of these samples. Okay, in here the M means a subset of n. So let us say these are n. So M means I select M which is less than n. So some batch, that's called batch, a selected set of samples, and obviously they come with the pair level also. So I will sum this only up to m, and that is why it's called stochastic, because the gradient I'm computing is based on some samples only. Okay, so hence in the gradient descent, I can define, let us say, superscript m to be the loss computed only on m samples. Okay, I compute this I equal 1 to m and gradient of L and f of x I. Okay, let's say j I. Okay, so I'm using double subscript. Okay, so j I and then w and then y I. Okay, j I. Okay, it should match the index of the x I j I. So that's what we are trying to do in the stochastic gradient. In the stochastic gradient, the trick is to just take small set of samples and then compute the gradient only on this small set of samples. And that is why, and also the fact that it's taken randomly. So I pick m samples randomly. So that's why it's called stochastic, because first of all the gradient. First of all, if I have taken all, then there is no concept of random anyway. Like all will be all only, so that will be the full gradient. But if I'm taking only sample and that too randomly, the gradient I'm computing is kind of stochastic. Okay, because I did not consider the full gradient, and that is the reason why it becomes stochastic gradient now, because the sum is over only the batch. Okay, the sum over a batch. Okay, the sum of the losses. The loss here in this case is written as j theta. Okay, so the details here are not written precisely, but this is over only those m samples. Okay, the loss computed over the m samples. Okay, so in this case, the j theta that I will define will be sum of I equal 1 to m. Okay, and then the grad of the small l x j I w and then minus Yeah, so what's the notation I was using? Comma yi, ji. Okay, so these things are hidden here, like I explained in the previous thing. So these things are hidden here. So j is now, so this outer thing is fine, but the j that is written here is for this guy. Okay, j. Okay, so and then once we have the stochastic gradient, so this is now behaving like a stochastic, not full. Okay, stochastic, not the full gradient. Okay, so that is why it's stochastic. That's the only difference. Otherwise, you do the same thing as you did in the same as in gradient descent. Okay, same as in gradient descent, but only thing is like this is now not the full gradient. Okay, this is not the full gradient, but it's now the stochastic gradient. Okay, so that is why it's called stochastic. Now there are like some ways to find to find the step length. So this is the step length, if you recall from our previous classes. This tells us how far to go in that gradient direction, right? But this is something we don't know. To be frank, there are some heuristic, like this is one of the heuristic, where you calculate the step length like this. Okay, so for the moment you can skip this, and you can usually like you can play with like 0.01 or something like that. Okay, in the stochastic gradient descent. Sometimes people also take just 1 over the iteration number. Let us say the iteration number is I for this for loop. Then they keep decreasing I. So there are many heuristic for this. So yeah. So this is the so-called stochastic gradient descent, and I believe we can stop here, and we will see some other variants of the stochastic gradient descent. For instance, Adam, and then RMS prop, and so on, SBCRG, and there are many actually proposed with varying degree of computing the gradients. And sometimes we have a problem of oscillating gradients, where the gradients, if you are in some kind of a valley, then gradients may go like this. So you may get an oscillatory behavior. So how do you correct those things, and so on? Sometimes you would like to benefit from storing the history of the previous gradients. Okay, so that you know which direction to follow. So the more details of this we will do in the next class. So I think I can stop here. This is the, and then I'm still not yet into the main neural network model. So that also I will discuss in the next class, where I will discuss the full algorithm of how to do the neural networks, backprop, compute the gradient methods with chain rule, and so on, so that we have a complete algorithm. And then we know how to compute the gradient, because gradient computation is like knowing how to do the backprop, because backprop is used to compute the gradient. So that's very important for us to know how to compute the gradient. And we will also see how to do that for RNN. So that will be the next class as well. So there we need BP TT, okay, backward propagation in time. So because the RNN have a concept of time. So these are the things we will see. So the main things in neural network is to know how to compute the gradient, and then obviously to know how to apply the variants of the stochastic gradient solver. This is the basic one that we have seen so far, but there are much better ones, okay, which converge much faster in practice. So this is something we will see in the next class. So basically we will cover the stochastic gradient part, and then later towards the end we will do the Newton method, and in general the steepest gradient method. That will cover Newton method, and also the stochastic or the subgradient type also we will see later. Okay, so with this I will stop, and if you have questions, then you can ask. Okay, so I will be here. Okay, thanks. And also the assignment 4 has been uploaded, and the deadline is end of November.